So I'd like to talk about the nomenclature used when working with phase diagrams. And I personally am not a big fan of giving everything a special name, because I'm much more interested in the physical properties of what's happening. But when you talk to other engineers, they're going to be using this language, and it's important for you to know it. So let's draw a binary phase diagram. Let's make a binary eutectic phase diagram. So we'll have temperature on the y-axis, the mole fraction of B atoms on the x-axis. So that will be pure A and pure B. So we're talking about a system with two components, an A component and a B component. And we'll draw a simple eutectic phase diagram. So again, high temperature, liquid, far A side is going to have a alpha solid solution, far B side will have a beta solid solution phase, and then we draw in our two phase regions, beta plus liquid, alpha plus liquid, alpha plus beta. It's worth commenting that a lot of times you'll find a phase diagram either online or in literature or in one of the reference books you have. They're not going to have all of these labeled. And oftentimes you're going to find yourself saying, well, what am I actually looking at? And what you're going to have to do before you can even use the phase diagram is to carefully go through and label the regions that you're interested in so that you know which is which. And the way to do that is to identify these single phase regions, for example, alpha, liquid, beta, and then to fill in the two phase regions because those are necessary. And sometimes you'll even find what looks like a mistake, and what it really is just a very, very tiny two phase region. So you might either find a blow up of that on the next page, or you might just draw it in yourself. But you know they have to exist. This is from the laws of thermodynamics. Anytime you have two single phase regions separated by another region, that other region has to be a two phase region. Or there has to be a two phase region. You can't have two single phases on top of each other, except for the very special circumstances of congruent melting. So, how do we talk about this? Well, these have names. The point, I'm going to change colors here. The point, or the line, where we have the first solid that forms, that is called the liquidus. Liquidus. The point where the last liquid disappears as we cool down, that line is called the solidus. The point where you have a single phase solid and you form a two-phase solid. So for example, as we cool down here, we start liquid, we make beta plus liquid, we make beta, and that down here we get some alpha precipitates that come out of our beta matrix. This line is called a solidus. And the same is true on the left side. It doesn't matter if it's A or B, it just depends on the transition going from liquid to forming solid, removal of liquid, and forming the second solid. In this particular phase diagram, we have another special point. That is this. In here, we have the formation of a eutectic microstructure. And this point, where this comes together, that's called the eutectic composition, E-U-T-E-C-T-I-C, eutectic composition. And the temperature, because the eutectic, focusing problems again. The temperature, where the eutectic forms, it has this horizontal line, and that temperature is called the eutectic temperature. Sometimes called TE for the eutectic temperature, is how we label it. So that's a eutectic phase diagram. Let's draw a peritectic phase diagram. So again, we have temperature on the y-axis. We have composition on the x, going from A to B, treating it as a ideal, two-component A and B elements, or A and B constituents phase diagram. Then here, that is our peritectic. Now this is a little more complicated than the eutectic, so let's fill in what we have. In the peritectic, we're necessarily including an intermediate single phase region, and that's right here. So on the left side, we have something which is going to be a phase that is primarily A. Over here, we have a phase which is primarily B. At high temperatures, we have a phase which is liquid. Great. Now, if we start looking at these, we can see, okay, I can start filling in some of these two-phase regions, right? So I know here, I must have alpha plus liquid. Over here, I must have beta plus liquid. But this region, I don't know what I have. And that's because right here, what I have is I have another single phase region. I'm going to call that gamma. And the way to think of this is you can think of it as there being some intermediate crystal structure or some intermediate composition, which is a perfect mixture of an A and B. For example, this might be say a B2 composition. So two atoms of B for every one atom of A, and that forms a different crystal structure. And it has a width to it, meaning that, okay, so it makes AB2, but it can take a little bit of A, and it can take a little bit of B, and it has a width to it. It's a solid solution. So if I do that, now here I've got alpha plus gamma, beta and gamma, so I've got gamma plus beta, and up here I have liquid plus gamma. So I've labeled all of the regions of my phase diagram. So we still have all of those Liquidus, solidus business. But what I want to point out here is, for one, that is eutectic. And in fact, if I wanted to, I could mask this off, and I could have simply a gamma beta figure. And I could have on the far left side AB2, and on the far right side B. But I didn't. So this behaves just like eutectic. This, however, is different. That is called a peritectic. I want to make sure I spell this right. Peritectic. That's a peritectic. And there's a peritectic temperature. It's a horizontal line that's associated with it. Now, what makes the peritectic interesting? What makes it interesting is that, over here, say we'll start over here, we start liquid, come down, we make alpha plus liquid, we come down, we make alpha, great, right? And we come down further, at some point we'll make a little bit of gamma, so it's going to be alpha plus gamma. We've seen that before. This region, we come down, we start liquid, we form alpha plus liquid. Now that liquid transforms into gamma, and again, we've seen this before. This is not a surprise. But right here, that little window, if I start out here, I cool down, I form liquid plus alpha. If I keep cooling, I now form liquid plus gamma. And then, as I keep cooling, I form gamma. So that, again, is going to be liquid going to alpha plus liquid, going to gamma plus liquid, going to gamma. What just happened was all of this alpha, which was a solid, all of a sudden has to be completely reabsorbed into the liquid, and it comes out as a completely different phase. So that is what makes the peritectic kind of interesting,